Hey everyone, and welcome. Today, we are diving deep into the world of flow processes. This is the core thermodynamic magic that explains how some of our most powerful machines, I'm talking everything from giant power plants to sleek jet engines, actually get the job done.
I mean, seriously, have you ever thought about it? You've got this insane amount of mass and energy just blasting through a complex machine at incredible speeds. How on earth do you even begin to wrap your head around that, let alone design for it? Well, the answer, it turns out, lies in understanding the energy of the flow itself.
So here's the game plan for this explainer. First, we'll nail down the difference between flow and non-flow systems. Then, we're going to uncover a kind of hidden energy that's super important. After that, we'll build the master equation, piece by piece. We'll introduce a crucial assumption that makes it all work in the real world, and finally, we'll put it all into action and look at some actual machines.
Okay, first things first. We have to get our heads around the two fundamental types of systems in thermodynamics. This distinction, well, it's the foundation for literally everything else we're going to talk about.
The core difference here is actually pretty simple. A non-flow, or what we call a closed system, is kind of like the gas sealed inside a piston. The amount of stuff, the mass, it's trapped. It never changes. But a flow system, an open system, that's our focus today. Think of water just gushing through a turbine. Mass is constantly crossing the system's boundary. It's coming in and it's going out. And that one simple fact, it changes everything about how we have to analyze energy.
Right. So since mass is constantly moving across that boundary in a flow system, it brings a special kind of energy with it, an energy that you just don't see in a closed system.
It's called flow energy. And honestly, the best way to picture it is to think of it like an entry fee. For a little packet of fluid to get into the system, something has to do work to shove it in against whatever pressure is already inside. And that work doesn't just disappear, it gets stored as energy in that fluid.
And the formula for it? It's beautifully simple. Pressure times volume, or PV. This is the work that was done to get that fluid into our system. It's the ticket that bit of fluid had to pay just to get in the door. So the big takeaway here is that any fluid that's flowing has this extra little piece of energy that we have to account for.
All right, now that we've got all our energy components on the table, let's actually build the total energy equation for a flowing fluid. We're going to do this step by step so it all makes sense. Okay, let's watch how this comes together. Step 1. We start with the energy the fluid already has on its own, right? That's its internal energy, U, plus its kinetic energy from moving, c²/2, and its potential energy from its height, gz. Simple enough. Step 2. We add our new player, that entry fee, the flow energy, PV. Now, step 3 is where the magic happens. Engineers notice that these two terms, internal energy U and flow energy PV, they pretty much always show up together. So to make life easier, they just bundled them into a brand new property called enthalpy, which we label H. This is just a brilliant shortcut that cleans everything up and gives us our final super elegant equation in step 4 for the total energy of that flowing fluid. And this really is why enthalpy is so incredibly important. It's a thermodynamic shortcut. It just tidies up all the math and lets engineers deal with really complex energy calculations way more efficiently. They just combined two forms of energy into a single, convenient property they can measure. Genius! So, we have our big energy equation. But to make it truly powerful for analyzing real machines, we need to introduce one more big idea. And this one is a real game changer, the steady flow assumption. So what in the world does steady flow actually mean? Okay, picture a smoothly flowing river. The water's speed might be different near the bank than it is in the middle, sure, but if you pick any single spot and just watch it, the speed at that spot stays the same over time. That's a steady flow. The properties can be different from place to place, but at any one location, they're constant. Now, the consequences of assuming this are massive. If nothing is changing over time inside our machine, that means the total mass inside and the total energy inside have to be constant. And if that's true, then there's only one conclusion. Any mass or energy that enters the system has to be perfectly balanced by the exact same amount leaving the system. It's a perfect conservation principle. What comes in must go out.
And this simple, powerful conservation idea, energy in equals energy out, is what we formalize into the tool that engineers use every single day. The steady flow energy equation, or the SFEE. This is the master key for analyzing pretty much every flow device you can think of.
And now for the payoff. Let's see how this incredible equation is actually used to figure out what's going on inside the very machines we mentioned at the start. This is where the theory hits the road. Just look at this breakdown. It's so cool.
For something like a heat exchanger, the main thing we care about is heat transfer, right? The SFE lets us calculate exactly how much heat is being moved. Now, for a turbine, the whole point is to get work out of it. The equation looks at the change in enthalpy and tells us exactly what the power output is. And for a nozzle, where the goal is just to speed up the fluid, the SFE tells us the final exit velocity. See? It's the same equation every time. We just focus on different parts to solve for what we actually care about for each machine.
And to make this completely real, the source material actually runs the numbers for a steam turbine. By plugging the conditions at the inlet and the outlet into our steady flow energy equation, the power output is calculated to be 298.8 kilowatts. So this isn't just theory, right? It's a practical tool that gives us hard, tangible numbers that we can use to build things.
Which, brings us full circle. The next time you see a plane slicing through the sky, you can actually picture the journey that air is taking. It's being compressed, it's being heated up, its enthalpy is skyrocketing, it's spinning a turbine to generate power, and it's being blasted out of a nozzle at incredible speed. And now you know all of it. Every single one of those steps is governed by the clean, beautiful logic of the steady flow energy equation.